Hi, I'm Isabel Rayas Fernández, and I will be presenting our work on learning equality constraints for motion planning on manifolds. Many robotic tasks require constrained motions, such as handing over objects between robots or keeping a cup or bottle upright while transporting it. One way of describing equality constraints such as these in planning is by using implicitly defined manifolds in configuration space. In this work, we focus on data-driven approaches to learning equality constraints for use in planning. In particular, we propose a new method called Equality Constraint Manifold Neural Network, or ECoMaNN. ECoMaNN is a neural network that models the zero-level set of HM of Q associated with a smooth constraint manifold. It takes a configuration Q as input and outputs a prediction of the implicit function HM of Q. For equality constraints, HM of Q is 0 for all configurations on the manifold. HM of Q is non-zero for configurations not on the manifold, in other words, for configurations that violate the constraint. Our main contributions are threefold. First, we introduce ECoMaNN, a neural network that aligns the subspaces of the approximated function with the subspaces of the training data. Second, we introduce a method for augmenting a solely on-manifold training dataset with off-manifold samples. And finally, we integrate the learned constraints into a sequential motion planner and show results for complex robotics tasks. ECoMaNN aims to align subspaces in the dataset with subspaces of the neural network. For example, consider a 3DoF robotic arm. The ambient configuration space is in R3. The manifold describing constraint on the end effector of the arm to stay on a line has a one-dimensional local normal space, as shown here on the purple axis. The local tangent space of that manifold would be the remaining 2 dimensions, spanning a plane tangent to the surface of the manifold. This is shown here as the green plane. The nearest neighbors of each data point, shown here in pink, can be used to approximate these spaces using local PCA. With the subspaces of the data computed, ECoMaNN then aligns the row space of the data covariance matrix with the null space of the network Jacobian, which must be equivalent to the tangent space of the true underlying manifold, and the null space of the data covariance matrix with the row space of the network Jacobian, which must be equivalent to the normal space of the true underlying manifold. Our training dataset is solely on manifold, and we set its label, or in other words the output of ECoMaNN, to be 0 vectors. For a more robust training of ECoMaNN, we augment the on-manifold data by projecting it off the manifold in the direction of the normal space vectors found during local PCA. We do not explicitly set labels for each of these augmented off-manifold data points, but instead we specify constraints on these labels via loss functions. We define 4 losses to train ECoMaNN with augmented data. First, for each augmented point, its target value is set to the augmentation distance. This loss minimizes the difference between the norm of ECoMaNN's output and the target value. The other 3 losses are Siamese or pairwise losses, which constrain the output value of 2 points relative to each other. The second loss enforces pairs of reflected augmentation points to have values of the same magnitude but opposite sign. This loss minimizes the sum of the 2 output values. The third loss enforces that a pair of points augmented from the same on-manifold point have proportional values to the augmentation distances. This loss minimizes the difference between the values normalized by augmentation distance. The fourth and final loss enforces that a pair of points at the same augmentation distance but originating from different on-manifold points have the same values. This loss minimizes the difference between the 2 values. Together, these 4 losses allow ECoMaNN to learn a robust approximation to the manifold's implicit function using both on and off-manifold data points. We evaluate our method on datasets representing 4 constraints: staying on the surface of a sphere, staying on a circle in 3D space, keeping the end effector of a robot arm with 3 rotational degrees of freedom on a line, and maintaining the end effector of a robot with 6 rotational degrees of freedom at a constant downward orientation. In the plane experiment, the end effector of a 3DoF robot is constrained to stay at a certain height. We use ECoMaNN to iteratively project configurations sampled from the ambient space onto the constraint. The graph on the left shows the projection success rate over training iterations of the network. ECoMaNN reaches more than 80% success rate after 15 training iterations. The plot on the right visualizes the learned level set of the neural network. We compare ECoMaNN to a variational autoencoder, which is a popular generative model that embeds data points as a distribution in a learned lane space, and new points can be sampled from the distribution. Our methods project samples with a much higher success rate than the samples from the VAE, as shown here. We then integrate the learning constraint into sampling-based motion planner. In this experiment, a robot arm must transport a cup to a green goal location, keeping the orientation upright throughout the motion. The path with ECoMaNN is very similar to a path planned using an analytically described constraint. Thank you.